This is the Openwheel. It's my open source DIY self-balancing board that I designed and built from scratch about 5 years ago, and I decided that it's time to revive this project. In the last Openwheel video, I did a teardown of this 4-kilowatt hub motor just to see how it works. If we're going to revive the Openwheel project and make it better, we need to understand how these work, and more importantly, we need to be able to test them. So today I'm going to build the first tool I need for this project, which is a hub motor dynamometer. While I'm building this dynamometer, I want to talk about the roadmap for this project. I also want to talk about the philosophy behind why I even decided to revisit this project. But first, let's move this out of the way and focus on the hub motor. To do my testing, I'm going to need to design and build something way more sturdy than this jig. The first thing that came to mind is to build an A-frame mounting structure, kind of like those bike trainers where you clip in the back axle and the wheel can spin freely. Honestly, I thought about just buying one of those and retrofitting it to work with this, but since I have a whole bunch of aluminum extrusion and a 3D printer, it would be way more fun to build my own. So while I jump on the computer and start designing this in CAD, let's talk about the goals for this new version of Openwheel. The first one is community owned and driven. This is at the core of this whole project. I already have a GitHub repository for the Openwheel, and as we build this thing together, that's the perfect platform to discuss issues and to do version control and all sorts of things. I want to be very clear that this isn't a product owned by me or by Bite Size Engineering or anything like that. I want this to be a community designed and community owned product. This also means that I can't do all of this on my own. We're going to need project collaborators, and we want to hear everybody's ideas on how to make this succeed. The second goal is that this must be easily built, modified, and fixed by a tinkerer or hobbyist. Yes, this project is going to require people with a lot of experience to design it, but when it comes down to actually assembling and building this thing, I want that to be as accessible as possible. And finally, I want all of the components to be reliable and easily sourced. On version 1 of the Openwheel, I went really cheap, and some of the electronics might be a little bit questionable. And one of the ways that we're going to make sure we have high quality components is not ordering stuff from AliExpress, but using reputable vendors like DigiKey. Here's what I'm thinking for the dynamometer frame. I need to go cut all of this aluminum extrusion and then assemble it over there on the workbench. Eventually, I would love for us to design our own open source hub motor, our own open source vest controller, and the aluminum rails that go on the side, and then the enclosure for the electronics. And then you need to have things like the footpad sensors and the battery management system, all designed by this community. And of course, we're not going to get it right on the first time, so we're going to iterate over and over until it becomes super reliable and enjoyable for everybody to build. The A-frame is assembled and everything is looking good, but now I need a way to connect the hub motor axle to these bearings. I have an M8 bolt that I can push through the bearings, but I don't have a way to connect the M8 thread to the M14 thread of the hub axle. Maybe I can create a coupler by welding these two different size nuts together. The first set of welded nuts actually worked pretty well. I was able to thread the bolt in just fine, but this gave me a lot of false confidence because the second one did not work out. I think I got some weld splatter inside the threads, and when I tried to force the bolt through, it actually ended up just stripping the threads. So that gave me an idea. What if I threaded in the bolt first and then welded the two together? That way I could back out the screw and have clean threads. Well, of course, when I tried to do this, I actually welded the bolt to the nut and I couldn't get it off no matter how much I tried. So I think I'm gonna scrap this idea and move on to maybe 3D printing a coupler. After a couple of iterations, I landed on this design. I paused the print at a specific height so that I could insert these M8 nuts and then continued the print until it was all finished. The captive nut allows me to tighten this whole assembly down together and gives me a pretty strong result. But once again, when I tested this out, it actually snapped one of the 3D printed adapters, so I'm forced again to go back to square one. Ideally, I'd like to machine this part out of acetyl machining plastic or aluminum, but I ran into issues with my machine and I wasted about a week trying to get it to work. For the sake of time, let's move forward and stick with 3D printing. I beefed up the geometry to make it a little bit thicker, and I printed this part out of carbon fiber PETG. With that, I'm finally ready to mount the load cell to see if I can get torque measurements when I spin up the hub motor. We're getting really close here, but as soon as I put on this torque arm or moment arm, I immediately regretted it. This is way too flimsy, it's not gonna work. So I need to come up with something different. But the good news is that this load cell does seem to be strong enough. And I 3D printed a bracket for the load cell module. So let's go ahead and install that and then figure out what we're gonna do for the moment arm. I know that everybody who builds an Openwheel will come from various backgrounds and skill levels. Some of you might be really excited about the prospect of ordering a blank PCB and all the components and doing the soldering yourself, while others might just prefer to skip that step. So I think my eventual plan would be to set up a website and sell completed assemblies. My vision is that somebody wanting to build an Openwheel will just go to a website, order the parts that they need, and then put everything together. If there's a particular part they're really excited about doing themselves, all the design files will be available for free, so they can go ahead and tackle that. Your experience building the Openwheel can be on a spectrum. It can range from just order all the parts and put it together and have it work, or go and download all of the design files, order PCBs, go to your own manufacturers, have all your stuff made, and put it together yourself. The builder gets to choose how far down the rabbit hole they want to go. Did that just fall in there? Crap. You saw it too, didn't you, on the camera, while I had my back turned. It's gone. Now I've got to slide this moment arm over the hub axle, put my little coupler back on, and slide this through here. Now I got to slide this little 3D printed sleeve over the load cell and tighten it down. And now I can attach the moment arm to the load cell using this 8mm bolt. So now when I turn on the hub motor and I apply a load, that moment arm is going to react to that load, and we're going to be able to measure that load really precisely using this load cell. Right now I have a 20 kilogram load cell on there, and if I find that that's too big of a range and I need to narrow the window a little bit, I also bought a 10 and a 5 and a 1 kilogram load cell. If I find myself in that situation, the load cell should be pretty easy to swap out. I'm excited because now I'm ready to move this over to the other workbench and connect it to the motor controller and spin it up. It's time to find out whether or not I can measure the torque and therefore the power produced by this hub motor when I apply a load. I've pulled up the VESC tool software and I've got a plot running of the current as well as the duty cycle. So let's go ahead and spin up the motor to a 50% duty cycle. But right now the motor isn't doing any useful work. We need to put a load on it or try to slow it down to see what it does in response and to see what kind of power we can get out of the motor. Right now the motor current, which is the red line, is about 3.5 amps. So when I apply a load, let's see what happens to that red line. You can kind of see it climbed up, and as I press on this and burn my thumbs, it jumps to about 6 amps there, and then when I let go, it comes back down to about 3.5, 3.4 amps. I would really like to stop melting my thumbprint, so in the future I want to add some sort of disc brake to apply a load to the spinning motor, or maybe I'll try to connect a second hub motor that will act as an electronic brake to try to slow it down. But the whole point of the load cell was to measure the torque produced when I apply the load. I spent a couple of days trying to get the VESC controller to read the sensor, but I couldn't get it to work. So if there's somebody out there who has experience connecting I2C sensors up to a VESC controller and plotting the data, please reach out to me because I would love your help. So this is where I'm at kind of a crossroads in this project, and I need your advice. I can continue to try to get this I2C sensor connected to the VESC controller so that I can read and plot all of the data right in the VESC tool, or I can connect an external microcontroller to the load cell and then write Arduino code to do all of this testing for me. The other benefit of using an external microcontroller is that I think I can get it to talk to the VESC controller using UART, and I can send it speed commands and really customize the tests that I want to run with this. That's definitely something I'm going to be more comfortable with, and it's more in my wheelhouse, but I was really hoping to get it to work in the VESC tool. So I'm kind of torn between these two roads. Do I stick with the VESC tool and try to get the I2C sensor to work in that environment, or do I abandon that and then go with what I know to work, which is an external microcontroller, writing my own Arduino code and really being able to customize these power tests? So if you have any advice on how I can get this to work, please let me know. So let's connect an external microcontroller to the load cell and plot the output. All right, so you can see that the load cell is currently hovering around 0, but when I apply a load, we should see that force change. There we go. So that moment arm is pushing against the load cell, and then when I let go, we can see that the load cell returns back to 0, saying that there is no power being produced by the motor. This is really exciting. It's really promising, the results that I'm seeing so far. Obviously, I have a ton of work to do calibrating this setup and getting real power measurements out of this motor, but I think I've got the mechanical systems pretty much sorted out. It got a little bit janky there at the end, but it works. And of course, I can always improve it in the future. Like I said earlier, if you're interested in contributing to this project or you just want to stay in the loop, the best way to do that is by joining the free Discord server using the link here on the screen. If you want to take it a little bit further and gain access to the full Discord server, you can do that by joining my Patreon. Here is a list of all of the current Patreon members, so if you want to see your name added to this list, go join Patreon today. That's it for now, but I definitely will have more updates on this project in the future, so be sure to subscribe so you don't miss those.